Greetings, everybody. This is the second video for part one of the chapter 10 lectures. And this video covers the angular and translational or linear quantities. The terms translational and linear in the language of physics, they mean the exact same thing. So don't let that throw you. And so remember that. And we're dealing again with a rigid object rotating about a fixed axis. In this case, here's this randomly shaped object. It's rotating about an axis through the origin, indicated by the blue dot. And remember, every point on that object will move in a circle, as indicated by this dotted line. And every point, remember, every point on this rotating object, no matter what the shape is, it's a rigid object rotating about a fixed axis. Omega, every point on this object will have the same omega. But notice that anything moving in a circle, again indicated by this dotted line, well, a point on an object moving in the circle indicated by a point on, let me just sort of babbling a little bit. So we have this rigid rotating object. There's a point on this object indicated by P. That's the point P. That point P is moving in a circle indicated by that dotted line. They haven't drawn the whole circle, obviously, but you get the point. Well, that point on the object will have a tangential speed in V, indicated by the red vector. Well, V is equal to r omega, where omega is the angular velocity or the angular speed, and r is the distance from the point P to the rotation axis. Now, every point on this object will have the same omega, no matter where it's located. But the tangential or linear speed, the translational speed, it depends on the distance from the point to the rotation axis. And V is equal to r omega, where in MKS units, that would be meters per second, obviously. R is in meters, and omega is a rad per second. Remember, rad or radian is actually unitless. Well, that same point on that object, it will also have an acceleration indicated in this figure. However, the acceleration vector, this purple vector here, it will have a radial or centripetal component directed towards the center. We know that from UCM. And it also has a tangential acceleration, AT, indicated by the red arrow. AT is the important one. And again, just like with angular speed, every point on the rotating rigid object has the same omega. Well, with angular acceleration, every point on the object will have the same alpha. But the tangential acceleration is equal to r times alpha, where again, r is the distance from the point to the rotation axis. And that's going to become important when we apply Newton's second law. Well, no, never mind. That's all right. So we have AT, the tangential acceleration, again, simply meaning it's tangent to the circular path that point is moving in. So AT is r times alpha, and V is r times omega. And the units of AT are meters per second squared. And the centripetal acceleration, we know from chapter 6, we know from UCM, the AC is V squared over r. But for what we'll see for the most part in chapter 10, the tangential acceleration is what's going to be important. And you can get the total acceleration vector A just using the Pythagorean theorem. And what they do is when they take AT squared plus that's a tangential acceleration squared plus the centripetal acceleration squared, just your the sides of your triangle, just Pythagorean theorem. Well, they get to this expression. They replace with the centripetal acceleration. They replace V with r omega, and that's how they get that expression. But that's not really that important. The main thing is that that the tangential speed V is equal to r omega, and the tangential acceleration AT is r times alpha. Well, let's look at an example. A very common example of how you plug a CD into a CD player, how does it actually create the music? And it's the music is stored on the CD, and it's stored in binary form, ones and zeros, and then the binary information is read by the CD player, and they convert the binary information to a sound file, like an MPEG file or what have you, and it reads that binary information with a combination of a laser and lenses. So for a CD player to work, and what happens is, you have the binary information is stored. One song is stored on the innermost part of the disc. Then as you go outward, it's track 1, track 2, track 3, and you go out to track 8 or 10, however many songs you have. But for a CD player to work properly, no matter where the song is stored, whether it's the inner track, at 23 millimeters from the rotation axis, or the outer track at 58 millimeters from the rotation axis, each that information, whether it's the song at 23 or the song at 55, they have to pass the laser lens system with the same tangential speed. Otherwise, it wouldn't be able to read the information. So each track has to pass the laser lens system with the same tangential speed, and typically that's 1.3 meters per second. So what happens is, because the linear or tangential speed is the same for each track, the omega changes. A CD player's designed so that it rotates at a different omega depending upon what track you're listening to, because each track has to pass the laser lens system with the same speed. And so we want to find the angular speed, omega, and we want to get the angular speed and just express it in revolutions per minute, because that's what we're used to. Revolutions per minute. How many revolutions does the CD make per minute? And we want to know what is the angular speed when you're listening to the first track at 23 millimeters, or the last track located at 58 millimeters. And those are the distances from the rotation axis. And then in part B, so in other words, I want to know, we'll call it, R1 is 23 millimeters. Our initial, excuse me. We have our initial is 23 millimeters, and then you go out to the last track, your R final is 58 millimeters. So I want to know my omega initial when I'm listening to the first track, and omega final when I'm listening to the last track. Then in part B, again, for a standard CD, the max playing time is a little over 74 minutes, 33 seconds. How many revolutions does the disc make in that time? And then over that same time period, which converts to 4,473 seconds, what is the angular acceleration of the CD during that time interval? So essentially, I want omega initial when you're listening to the innermost track, omega final when you're listening to the outermost track. That's part A. I want to know if you play the whole CD, how many revolutions does the CD make? And then what is the angular acceleration as you're listening to that CD? Well, let's look at part A. Well, we want omega initial and omega final. Well, remember, if V is equal to R omega, we know that the linear speed is equal to R omega. Well, omega is V over R. And remember, for a CD, that linear speed is the same for each track. So omega I is V over Ri. Plug in the numbers. Remember, the V is the 1.3 meters per second. R initial is the 23 millimeters, which is 10 to the minus third, 23 times 10 to the minus third meters. And you get omega initial is 57 radians per second. Just convert that to revs per minute. Nothing complicated. Radians per second, there's 1 rev in 2 pi radians. and there's 60 seconds in 1 minute, and you get 5.4 times 10 to the second revs per minute. So it's 540. But yes, that's a lot. Now let's get omega final. Well, omega final is V over R final. And remember, R final is the 58 millimeters. Nothing complicated. Convert to meters. Remember, V is the constant, 1.3 meters per second. You get 22 rads per second. Convert rads per second to revs per minute. 22 rads per second times 1 rev in 2 pi radians, 60 seconds in 1 minute. And you get 2.1 times 10 to the second revs per minute. Okay, now we need to get, for part B, I want to know how many revolutions does the disk make during the entire time that it's being, if you play the entire disk for 74 minutes and 33 seconds. Well, to get the revolutions, I first need to get theta in radians and then convert it from radians to revolutions. Well, I know T is the 74 minutes, 33 seconds. And I know omega initial. And I know omega final. So which kinematic equation do I want to use to get theta? Well, look at the fourth kinematic equation. And again, usually we can set theta initial equal to 0. So I know omega initial, I know omega final, I know T, I can get theta. And I'm going to set theta initial equal to 0 and drop the subscript. So I'm using the fourth rotational kinematic equation. Theta is 1/2 omega I plus omega F times T. Well, T, you want to convert it to seconds. It's 4473 seconds. And let's get theta. Theta is 1/2 omega I plus omega F times T. And you get an angle of 1.85 times 10 to the 5th radians. Convert that to revolutions. And here's the conversion. There's 1 rev per 2 pi radians. Remember, 2 pi is a complete circle, i.e. 1 revolution. And you get 2.8 times 10 to the 4th revolutions. Then in part C, I want alpha. And again, I know omega initial, I know omega final, I know T. So I'm going to use the second rotational kinematic equation right here, because I know omega final, I know omega initial, I know T, and I'm looking for alpha. So why not just take the second rotational kinematic equation and solve it for alpha? So you get alpha is equal to, again, the basic algebra. I took rotational kinematic equation 2 and just algebraically solve it for alpha. You get alpha is equal to omega F minus omega I over T. Plug in the numbers, and we get a negative 7.6 times 10 to the minus 3rd rads per second squared. Well, it makes sense. If you listen to the innermost track first, and just go to and listen to the outermost track, your omega is decreasing. It's a negative angular acceleration, because the CD, the rotation. I didn't mean to do that. There we go. But yeah, so alpha is negative, which is fine. And the main thing is V is R omega. That's the tangential speed of the point on that rotating rigid object, and the tangential acceleration. So V is R omega, AT is R times alpha. And again, with this example for CD, because that binary information passes, through through the laser and the lens system, each track has to pass under, through the lens and the laser. It has to pass at the same linear speed. So V is the same for each track. Hence, the CD will rotate at a different omega depending upon what track you're listening to. Yeah, so that's the second video for the Chapter 10 Lecture Notes Part 1. Let me go ahead and save this and get it posted.